Okay, so as we were saying, during a dilution, molarity goes down and volume goes up. And so normally during a dilution, molarity 1 will be greater than molarity 2, and volume 1 will be less than volume 2. And so that's what you should expect. And some examples of how we can actually do dilution problems follow. So say if you have 100 milliliters of 2 molar sodium chloride solution, and you want to make it 0.65 molar. Let's see, what should the final volume be? All right, so again, we use our equation M1V1 equals M2V2. That is the base equation, but very often we will have to rearrange it. In fact, most of the time we'll have to rearrange it to solve for the term that we want to find. It actually makes sense in any given example to distinguish explicitly what is what. So the M1 would be the, let's see, M1 would be the original molarity, the molarity you're starting out with, which in this case is 2 molar. And volume 1 would be the volume of the solution when it has that molarity. And that was 100 milliliters. Now in this equation, you may have noticed I wrote down the volume in milliliters. And the fact is that it's okay to use milliliters for the volumes in this equation. You don't have to change it to liters. It's just that if one volume is in milliliters, then the other volume has to be in milliliters also. And in fact, this equation works for any volume unit. You could use cubic feet for the volumes if you wanted to, as long as both units are, or both volumes are in the same units. So milliliters is actually okay for this equation. M2 is the last, the final molarity that you want to achieve. And that was 0.65 M. And V2 is the final total volume of solution. Okay, so that is the unknown in this equation. So we need to solve this equation for V2. In order to solve for V2, we essentially want to get V2 alone on the right-hand side of the equation, which means we have to move M2 to the other side of the equation. You can get rid of M2 on the right by dividing the right-hand side by M2, and that cancels out. But to keep the equations, the two sides of the equation equal, you have to divide by M2 on the other side also, to keep it equal. So essentially, M1 V1 over M2 is what V2 is. And now if we just take those quantities, M1 is 2 molar, V1 is 100 milliliters, and M2 is 0.65 molar. Notice that the molarity cancels, and that leaves you with milliliters as a unit, which is a volume unit, which is what you're looking for. And let's see, 2 times 100 divided by 0.65 gives us 308 milliliters. And again, V2 is the total final volume of solution. Okay, and in practical terms, you often want to know how much distilled water you need to add to a solution in order to accomplish a dilution, because that's how you're actually going to do it. You're going to take some distilled water and add it to the solution. So you want to know how much. Okay, so how much water that you have to add to the solution is just the difference between V2 and V1, because V2 is the final total volume of the solution, V1 is the original volume of the solution, so it stands to reason that volume added would have to be V2 minus V1. Okay, so V2 is 308 milliliters minus 100 milliliters. Oops. And that is 208 milliliters. So you add 208 milliliters to the original 100 milliliters, and you will achieve the dilution we wanted to achieve. Okay? For another example involving molarities, we could ask what volume of 6.00 molar NaNO3 should you use to make 525 milliliters of a 1.20 molar solution. So this is unusual in that V1 is actually the unknown. So in this equation, we still have the equation M1 V1 equals M2 V2, and M1 is the first molarity mentioned usually. It's the molarity you're starting out with, which is 6 molars, a molar in this case. V1 is the volume of that solution. Actually, it's saying what volume of that solution should be used. So V1 in this case is the unknown. M2 is the target molarity. That's 1.20 molar. And V2 is the volume of that solution, which is 525 milliliters. All right, so this time we're solving for V1. And well, we do it pretty much the same way we did in the last example, except it's M1 that has to go on the bottom of the other side now. V1 is M2 V2 over M1. And so that means V1 is, M2 is 1.20 molar. V2 is 525 milliliters. And M1 is 6 molar. So notice again that molarity cancels out, leaving us with milliliters for a unit. And we end up with 105 milliliters. That's the volume of the 6 molar solution. We should dilute to 525 milliliters in order to achieve a molarity of 1.20. Okay, one other example. If you take 85.0 milliliters of a 0.425 molar solution of copper 2 sulfate, and you dilute it to a volume of 250 milliliters, What is its final concentration? All right, once again, M1V1 equals M2V2. M1 would be the 0.425 molar solution, and V1 is the 85 milliliters. M2 is the unknown. What is its final concentration? And the volume of that concentration is 250 milliliters. So this time we're solving for M2. Well, that just means you bring V2 to the bottom of the other side to get M2 alone. M1 V1 over V2 is equal to M2. And let's see, M1 is 0.425 molar. And V1 is 85 milliliters. And V2 is 250 milliliters. Notice this time, milliliters cancel, leaving you with moles as the unit, or molarity rather, as the unit. And it works out to 0.145 molar. And also keep in mind what I said at the top of the page. During a dilution, normally volume goes up and molarity goes down. So whatever you end up with, it's almost certain that M1 should be greater than M2 and V1 should be less than V2. And here, let's see, we found M2. M2 should be less than M1, and it is. M1 was 0.425, M2 was 0.145. And notice how also the volumes relate to each other. V2 is greater than V1. And so that's something that's useful to keep in mind as you're working these problems, to kind of check your answer. Okay, we can use molarity in stoichiometric type problems too, because we're often concerned with the number of moles of various things in a reaction and how they relate to each other. Well, you can find moles from molarity and volume. So if you're doing a reaction in solution, molarity times volume might be a useful way to find moles. Okay, so solution stoichiometry is what this is called. So molarity allows us to convert mass to mass in reactions that occur in solution. But you still have to go by way of moles. So for example, you could go from volume of A to moles of A by using, number of moles is equal to molarity times volume and rearranging that to find number of moles. Then you can use the stoichiometry in the equation to go to moles of B. And then you can use, number of moles is equal to molarity times volume to find volume of B. But you still have to go by way of moles. That's important. So for example, what volume in milliliters of 0.150 molar HNO3, nitric acid, will react completely with 35.7 milliliters of 0.108 molar sodium carbonate? Okay, so nitric acid is an acid, sodium carbonate is a base. They undergo a reaction according to the equation Na2CO3 plus 2HNO3 will yield 2 NaNO3s and CO2 and H2O. Generally, whenever you can combine carbonate type compounds with an acid, you get carbon dioxide and water. So it's basically a bubbling solution. This is basically the reaction that goes on in Alka-Seltzer. Alka-Seltzer is sodium hydrogen carbonate, but it still has carbonate ions in it. And it reacts with some citric acid, which is in the tablet, which is what makes it fizz. And so you put it in the water. The citric acid and the sodium hydrogen carbonate, or sodium bicarbonate as it's better known, will dissolve in the water. They react with each other, and you get, let's see, in that case, it would be sodium citrate and carbon dioxide and water. And it's the carbon dioxide that comes fizzing out of the water as bubbles. Okay, so we've got our reaction here. And in order to find the answer, we first have to go through moles. So the first thing we need to do is take the thing where we know both the molarity and the volume and find moles of that thing. So we first want to find moles of Na2CO3. Okay, the moles of Na2CO3 is going to be the molarity times the volume. And we've got a molarity of 0.108 moles per liter. And we've got a volume of 35.7 liters. Oh, sorry, milliliters. And that comes out to 0.0357 liters. And that means that we have 0.003856 moles of Na2CO3. 0.003856. Okay, the next step would be find moles of HNO3 that react with that number of moles of Na2CO3. All right, so that's 0.003856 moles of Na2CO3. And the equation says it takes 2 moles of HNO3 for every 1 mole of Na2CO3s. and that gives us 0.0071711 moles of HNO3. And if we want the volume, that's just number of moles divided by molarity. So the number of moles of HNO3 would be 0.007711 moles of HNO3 divided by the molarity of the HNO3. The molarity of HNO3 is 0.150, which means 0.150 moles per liter, or 1 liter for every 0.150 moles. Notice this way, moles of HNO3 cancel out, and you get volume of HNO3 in liters. And that's 0.05. Oh, wait a minute. I may have made a mistake in the math, so let me check. Okay, divided by 0.150, and that's, oh yeah, okay, no, that's right. 0.05141 liters of HNO3. And to change that back to milliliters, you just divide, multiply by 1,000. And that ends up being 51.4 milliliters of HNO3. All right. So that's the kind of problem you can do with stoichiometry. The next section is about types of aqueous solutions and solubility. Okay, so all solutions are homogeneous by definition. But other properties can differ from one solution to another, even if they're, actually both, homogeneous solutions. There are properties that can vary from one solution to another. And that usually depends on the properties of the solute particles. There is a certain process for dissolving something in a solvent, and there are more or less 3 steps, and they don't occur normally in any particular order. They occur more or less simultaneously, and those 3 steps involve getting the solute particles apart from each other, because the solute particles are normally solids, maybe liquids in some cases, But either way, the particles have a certain attraction for each other, which is why they're not gases. You know, it's solids or liquids by definition. The particles have a certain attraction for one another. So in order to get them to mix into a solution homogeneously, you have to get those solute particles apart from each other, and that takes a little bit of energy. At the same time, you also have to get the solvent particles apart from each other. The solvent in most cases will be water, and water molecules are fairly strongly attracted to one another. So you have to get them apart from each other, and that takes a little bit of energy. And then you have to establish an attraction between the solute and solvent particles. And at that point, if you're able to do that, that releases energy. And so the overall process can either end up taking in energy overall, or it can release energy overall. If the process releases energy overall, then that means that it's probably a substance that dissolves in water very easily, like sodium chloride. The process of dissolving sodium chloride in water would release energy overall. On the other hand, if it's a process that takes in energy overall, then that's something that might have a more difficult time dissolving in water. And it might need, for instance, you might need to heat it up in order to get the substance to dissolve in the water. Anyway, I'll write out the three processes now. So step one, although, like I said, these don't necessarily occur in this order, they occur more or less simultaneously. So number one is you have to overcome the attraction between solute particles. Number two, you have to overcome the attractions between solvent particles. And then third, you have to establish attractions between solute and solvent. Okay. Very often, the last step is the hang-up. There are a lot of substances where there just isn't enough of an attraction between the solute and the solvent to sort of compensate for the energy you have to put in for the first two steps, and the substance just won't dissolve in water, or the solvent, whatever the solvent is. The process involves, this third step here involves hydration. Hydration is a process in which the solute particles are surrounded by, well, if it's in the case of water, H2O molecules. And that has the effect of stabilizing the solute particles in the water. And it also allows the solute particles to move around freely in the water. And also it allows the solute to move freely throughout the solvent, because basically the solute particles are surrounded by solvent particles. So as they move through the solution, the other solvent particles just see the solvent particles that are surrounding the solute, and they don't even know the solute's there for the most part. So for example, when sodium chloride or other ionic compounds dissolve in water, they separate into ions. So sodium chloride becomes Na plus ions and Cl minus ions. The Na plus ions will be surrounded by water molecules, and water molecules, I've mentioned this before, but just as a reminder, water molecules are bent like this with two hydrogens. And the oxygen has a greater attraction for the electrons in these bonds than the hydrogen does. And so the oxygen pulls electrons closer to itself and further away from the hydrogens, which means that you get a partial negative charge, and that's what this symbol means. It's the Greek letter delta, but it means partial negative charge on the oxygen end of the molecule. It's not a full -1, it's maybe a -0.6 or something like that. And you have a partial positive charge on the hydrogen end of the molecule. And what happens when a compound, like say an ionic substance like sodium chloride, dissolves in water, the Na plus ion has a positive charge on it, and in order to stabilize that positive charge, the H2O molecules will gather around the Na plus ion with the negative oxygen end of the molecule facing the sodium plus ion. So the negative charge on the oxygen, partial negative charge that is, helps stabilize the positive charge on the sodium ion. And so you end up with water molecules surrounding the sodium ion on all sides. This is actually a three-dimensional process. Since the charge on the oxygen end of the water molecule is only a partial negative charge, it takes several water molecules to sort of cancel out the +1 charge on the sodium ion. And I think the actual number is 6, but I could be wrong. The opposite happens with the Cl minus ion. Since the Cl minus has a negative charge, the water molecules gather around it with the hydrogen side, that is the partial positive side, towards the chloride ion, like that. And again, since the chloride has a full -1 charge, and the hydrogen ends of the water molecules only have a partial positive charge, it takes several of the H2O molecules to stabilize the negative charge on the chloride ion. Now that the ions are completely surrounded by water molecules, they're able to move freely throughout the solution, because they're surrounded by water molecules, and the other water molecules out here in solution will just see the water molecules that are surrounding the ions. And so, they just interact like they normally would. And this is, again, the process of hydration, that is stabilizing the charges by surrounding the particles with water. Some substances that don't dissolve because they are, say, small ions that have large charges on them. And in those cases, you may not be able to fit physically enough H2O molecules around the ions in order to stabilize them through hydration. Generally, only ionic and polar substances, and we haven't really gone over polarity of molecules, we'll get to that in a while, but generally only substances that are ionic and polar covalent molecules will dissolve in water. And that's because water is also polar. And the old saying is like dissolves like. Polar solvents like water will generally dissolve polar or ionic substances, and non-polar solvents like gasoline will only dissolve other non-polar substances like like oil or another nonpolar substance like maybe wax or something like that. Wax will dissolve in gasoline, but not in water. On the other hand, salt will dissolve in water, but not in gasoline. And so it's basically like dissolves like. And so nonpolar substances, like oil, don't dissolve in water. But it's important to keep in mind that actually not all ionic or polar substances will dissolve in water either. So it's only actually some ionic and polar substances that will dissolve in water. Nonpolar substances, though, no chance, not going to happen. And we'll go into that in more detail next time, but I see we're up at our time limit, so that's going to be all for today. Bye.